Today we're going to talk about simulation and verification. We had now the overall workflow and we had the different design blocks. So the question is now, how do you check that those work? In the overall scheme, we're like half time. I'm still debating if we switch the next 2 lectures around to have like another design block and then another part of the process essentially, because it maybe makes more sense for the assignments. But that, I mean, it doesn't concern you too much because you will just see the solution in the end and how it's being done. So, lecture goals for simulation and verification. As usual, written a few down. There's the question, of course, we had in the very beginning of the lectures of the course, we had simulation levels. So we're going to go through those again, / in more detail, what they are used for, and then there come various topics on how can I be, overall I try to answer the questions of like debugging efficiency, simulation speed, how can I get automatically reports, what verification metrics do I have, and how can I generally automate my workflow more. What we will touch today in the lecture, but will then mostly be covered in the seminar again because it's in the tool itself to do the workflow. There's beautiful slides today with a lot of blocks. We have 3 different levels, which are the first level we already know, we have already worked with, is a behavioral / functional simulation. It's just a very simple where we just code. Oh, wonderful. Can I just go into Teams and, no, can I? So, we're gonna cut this out. No, I will cut it out, fine. We have the behavioral and functional level is basically just representing literally the code into simulation and give the results from that, so not considering any logic components or anything, or any delays. Post-synthesis is then already the translation of the code into logic elements, and then the post-place and road also / implementation simulation is basically for when the design is on the chip and you know all the distances between the different components, and then also timing delays and those kind of things, and propagation errors and those kind of things are considered in the simulation. So basically from the first one it's just like functional, how we intend the design, and the last one is then actually on the level which actually is very, very similar to the chip, and actually in many cases if your test benches are correct and you do the rest of the verification correct, you do not need to do hardware tests anymore. It's generally still done because you never know if your test bench ends on 100% correct, but that's the philosophy essentially. Behavioral simulation is used to verify intended functionality of the design. Use of the design entry to just check if I've written my code directly. So if my idea of my logic is correct. Key points are that the inputs are fed into designs and the outputs are checked for correctness. How this is done we should look into today, and this does not account as said for any hardware delays, propagation delays, hold on setup times of signals. All these kind of things are not considered. So everything when I do signals in parallel, they all arrive at the same time / are not considered for the next line for the other signals. Post-synthesis simulation already also the behavioral simulation of course is the way by far the fastest simulation. So it's the way to go to just check if I'm coding correctly. So anything else is not really advised, and the other steps are not really advised to be used for the simulations. You might also go at any point back to the simulation, because if you figure out you have like a layout problem or something like this, you change your code, of course, and you move it around. You might want to first run the behavioral quickly that you do not have programmed a new error into it. Otherwise, you run your implementation run and it takes forever, and you realize, oh damn, I actually made a different mistake now. Post-synthesis is a step in between, which basically aims to check if your synthesis tool translates your logic, your code correctly into logic elements. So that basically the synthesized logic matches the functional intended logic. And this will not give me more precise like timing delays or something like this, but it makes sure that my things work correctly. And this, for example, where automatized testing is very, very strong, because if my behavioral works, I can just run this one automatically, wait for the result of it, and then move on. Also, I see much better like any like delay / resource consumption. So after I've done the synthesis, I might run the simulation as well on this level to see how long things take. Yes, I think I covered. The other part is the simulates the netlist generated from the synthesis, so the result out of the synthesis. So it's not anymore code itself. That's the key point here. The next important one, but is often also avoided, is the post-implementation simulation. It is great because it simulates the entire design when set up correctly. So it requires a lot of constraints and those values correctly. Allows to fill in the timing information. So you do not, it is like in the chip, ideally with the perfect simulation tool, you would, in the perfect setup, you would not need to test on hardware, but also it takes a significant amount of time. And that's why many people then rather put the design onto the chip and test it out in hardware than doing the simulation. But the simulation also considers for worst case scenarios of timing delays. And then, of course, you would not end up with a verified scenario. You just end up with your chip specifically working in your design when you do a hardware test. So if you want to do a rollout of your design onto a lot of chips or for space graded, where you have very high standards of verification, you want to do this kind of simulation because you can make sure that it will work on any chip which you will get. Because basically this considers the worst case chip manufacturing essentially. So exactly, it verifies on actual FPGA hardware, parasitic delays, routing delays, other effects, whatever you have in your chip. Basically, besides a timing report, this can be used for timing closure. So saying I, in fact, can reach that operation frequency of 50, 10, 100 megahertz and so on. So that's your tool to say that my design actually works. If you cannot show that your design works in here, but it works on a chip, then you go into the risk that, so on your FPGA, on your board, you run into the risk that the next batch of boards or something will just not work because of the manufacturing differences in the designs. So maybe you have coincidentally very, very good FPGA, very good quality, then it's good, yes.
Question, you said behavioral simulation is the fastest one. Now,
yes.
how does it scale? How long does a post-synthesis simulation take and how long does a post-implementation simulation take?
That's a good question. I don't think you can generally assess that. It's definitely multiple times longer. It's not like a percentage. I would say at least like for the post implementation can definitely be 4 times as long, but it's very hard to say. It depends on your tool, depends on the license you have, because often the standard license for simulation is limited in performance. Maybe you actually say in behavioral simulation, I simulate everything, but in here I have verified blocks. I do not need to simulate them. We will come to that, how you can spread out your design to make it a bit more efficient. But of course, this is basically something which will run for a day or longer, and with a bigger design that you just let it run through. You do not want to touch this multiple times. It's a verification process almost. So you get much faster, you get behavioral simulation and a timing report. And if these two work out, we have not covered the timing reports, but we will in the next, or the lecture after. And there you will see if you have a delay, which is a problem on any other signals. The simulation is just on top of that doing the same and showing you if you actually get the same result, if you have missed anything. So this is not going to be run very often. For our designs, I do not intend that it takes a day.
You said it can take a whole day.
Or longer.
Why is it so? Isn't it just running it like a real application, but just checking metadata?
You need to consider that already in behavior simulation, it can get quite slow because if you have a big design, you have, I don't know, hundreds of thousands, whatever, of signals, which need to be for every time step, need to be simulated. And when you then put not only the signal on and off, but also propagation delays where it needs to consider design into, then this complexity scales, right, with the amount of signals, and that's when you get a lot slower.
So basically brute force is everything that can happen.
Yes, pretty much, if you want so, yes. I mean, not everything which can happen, but it simulates what I have what I stimulate as input. So I give an input, and that propagates through my logic, and it will brute force the worst delays, parasitic delays, and so on there. Yes, so it basically puts essentially, if you want to put it badly, it puts a margin on the delay of the signal based on your design. And that, of course, can take an extra time to calculate. Oops. Did I? Okay, interesting. Forgot here one point. Here, the other part is that you basically do this mostly for high-speed clock designs. When you, for example, there's a way that you can, that a propagation, you can allow it to take multiple clock cycles. What a timing report does, it checks if I match the timing constraints. But I may assert somewhere a signal for multiple clock cycles, even though I need it earlier. Then, of course, this can lead to issues, and when you will do these kind of things more when you go for higher performance designs. And then you just want to be sure that your things work. And the annoying thing is most likely you will not see this in an actual hardware implementation, but again, at some point you might run into issues. Coming here to so that's the simulation types, and for all these simulations, essentially, the simulation setup is very similar. I actually just realized that, design constraints, but design constraints I did not put in, we could have put into here in the setup for the lower level, the later stages simulations, but we're going to cover that in the place and routing with the timing and everything together. Makes much more sense than here. We have 3 parts essentially. Well, the test bench accommodates the last 2 ideally, but there's also ways that it's not in there for efficiency reasons, for simplicity reasons. So you have a test bench, signal generation, and a result checking. The test bench we already had essentially is a module which we have designed, which provides a stimulus or input signals and contains the design under test, unit under test, DUT or UUT, and the monitors as output. That's essentially the overall definition. That's what you do. You have already seen in the assignments that the simulations just run through. It provides an input. In our cases so far, you see the simulation as just a waveform, but what we also try to do in the future is, and the next one is actually automatize that we do not have to look at the waveform anymore. That's going to be the next assignment. And you only look at the waveform to debug, to analyze this design if it's actually in detail as I want it to be. But the design gets bigger and bigger and bigger, and then you cannot just check everything out by manually, and you miss things because human error. Purpose automates testing by applying series of inputs and checking against the output. So you want to really make this efficient and well coded. A test bench will take significant effort, a good one to do. Consider significant effort, especially also consider toward this design. The more complex my design is, the more scenarios I have, the more inputs I need to simulate, the more responses I may have. Those kind of things can quickly get quite big. And that's also why it's quite important we're going to come to this later, to break down your design into smaller steps, unless you're at the very end. Structure. I said it contains this unit under test, can also be actually multiple. So it can be on a certain level, it can have multiple units, but there's one core unit on the test. But it can simulate other parts like a SDRAM or whatever input, or Ethernet or whatever can be simulated in here as well. But that is almost an input signal, but you have it not from one direction, right? You have my trigger, my user interface, but I also have other interfaces like my memory, my Ethernet, my display, whatsoever, right? When that's like here, is that a signal generation? Is that a unit under test? Depending how you define it. And then there's result checking, just to, again, get the response again. For the signal generation, of course, 2 obvious ones are the clock and the reset signals, unless you do not have a synchronous design, a clock design, which is rare, but can happen. For the last assignment, I tried to make without clock, but I was annoyed in the end, so I didn't. So clock and reset signals is always being set up, but it's also very simple to do in the simulation, so that's not a problem. More complex it can get here in the input stimuli. which are mimicking the real operation. Because here you need, depending on what you do, you may just send like byte after byte. That's already quite simple. But on top you might have a communication protocol. You might have whatever other information, and that will then quite stack up into a bigger thing. So you need to think about how you want to design a test bench. And there's always here the solutions, always the approach how it goes. At least for me, it goes actually like this. First, I put hard-coded values, so I see if it works with what I imagine right now. I change this manually. When my design gets a bit bigger and I want to test other things, I put random values in there. And when I realize, oh, now I need to change 1,000 lines to change my design, then you start using test vectors, so files which contain data or images or whatever to be simulated. Otherwise, you have to go through your code and change everything. So kind of the more your project expands, the more you change this. Ideally, of course, you would consider the test vector and how this all looks in your design design draft phase. So in a preliminary design, when you draw out the architecture, when you're experienced enough, you know what design blocks you want to have, you know what simulation blocks we have, what do I need to simulate, how do I need to simulate it, then you draft it all out, you make work packages out, tasks out of it, and then on to-dos, and then you do not go first to the simple, annoying thing. You try to overall write it a bit bigger. So it's more efficient in the long run. Otherwise, you have to rewrite your test bench 1,000 times, and it's annoying. Yes, although it can still happen because your design files might change, and then you need to change your test bench again. So it might be actually a loop, but in a more advanced experience stage, you want to, of course, avoid that this kind of loop. Also, when you have proper requirements, you will have to generate the signals in a certain way, and you may not be able to change it. So if I know I get Ethernet data in, I will need to have a test bench which simulates the Ethernet protocol. There's nothing I can do about it, right? That's set. So I have to write a test bench which sends me the Ethernet data, and I need then to properly accommodate that. Result checking. There's a thing called asserts. We will look into that in the seminar. Basically, that will automatically check for expected outputs and can then flag if it's the expected output or not. And you will get an error log of that. So it's quite useful, or like a message log. Here's also, we're going to come to the self-checking test benches, which basically automatically compares the design under test output to the expected output values. So it basically tells me automatically this is as it should be or not. To which level you do this is always something how much do you care in detail about the responses, how many responses do you can have. I make a communication responses, but do I want to consider also all the error scenarios which may happen or whatever? This really depends. Also on maybe I get an IP core from someone else, which I know it's verified, then I will not bother with doing self-checking for this as well. But then how do I test the rest correctly? Yes, coming now to some verification approaches. It's very small here now, but just for completeness on one slide. I could have actually written each of them in one line instead of the subpoints, I guess. But yes, there is 6 types. I mean, it depends always. Everyone splits them a bit different if you go to different sources. But overall, these make sense. That's why I went with those, for example. But your terminology may vary depending on the company, on the standards, whatever you talk about. From the top, we go from very simple coverage methodologies to the most complex one. And we'll quickly walk through that. The statement coverage as well as the block coverage essentially covering the design just line by line. In one statement, so statement by statement, which is line by line, and the other is block coverage, which is blocks exist out of lines, right? So it's very similar. So you just check if your simulation touches each block in each statement or each statement of your design. So you just go through that. Conditional expression coverage is basically the results, the percentage which I get out. So code coverage is always a percentage of code. is the ratio of number of cases evaluated to the total number of cases present. So I want to know, do I go into every case in my design? And this is just the written lines. I think, as far as I understand this one, this is just the written lines. So if I have case 1, 2, 3, but technically I have more cases defined, and I just do others, then this will be those considered. In the branch and decision coverage, it will also consider any true or false. So sometimes you do not write necessarily all of them down in your code, but it will also consider these kind of things, which are lacking. So this is already much more detailed, you see, because it will go in each combination of each if-else, and that works. So this gives already more information, and then you have a toggle coverage, which basically is less of an code itself coverage. It shows the activity of your signal. So do I have in my design states which are never activated or deactivated or only very few times? And this will give me a very good insight into how good my code is, how much activity some code areas have, and this might enable me to, why is this not even be activated? It should be, or, I wrote this at some point for some scenarios, but I never use it, so you can throw it out of your code, and then you use less resources, right? Which makes my timing and my performance maybe better. So this very, very powerful tool here to go in. So it basically measures design activity in the design. Can even be constant values, which I do not change, or something like this. So basically it could be signals which stay constant, because I never have changed them, or I changed them only once, and never again in initialization or so. So I like this one. It's very, for efficient design, it's very powerful. And then, of course, the code coverage, which is the most important one / the really complete one. Complete, we're going to come to that in a second, is the full state machine coverage. So it is literally a full design, reports whether simulation reaches all states which are potentially even reachable. So all combinations is a bit similar to the branch and decision coverage, but it goes over all transitions as well, and each loop or whatever of state machine I might have. So it just tries to get everywhere in the design, which may bring up the question actually for the next slide. Limitations. I'm sorry, it's a lot of text, but I wanted to have it written down so the definitions are there. So in general, it's an important indication for us. So the code coverage, we will see how much code we test, how much activity we have. So basically, but it shows just how well the design code has been executed, how much of it does not know anything about design, does not know any functionalities, no insight on missing parts. If I just something missing, I mean, I guess, is it covered or not? You just miss something, you're missing something. Can't cover that. And then assessment of the quality of existing code is also not being done. Should have maybe not there. So it just literally says, well, it's the quality of the existing code if it's being executed or if it's efficient, if it's being used often, or if the reuse of the code is often, but it doesn't show the efficiency of it. So it's a quality assessment in the sense of, do I have any unused code? Do I explore something not? But yeah, I have already written down here as quantitative statement. And of course, something missing is also kind of redundant here with non-implemented features cannot be identified. Like my code coverage will go in there. If I do not check for my functional response, I mean, then I will just not know if I ever had anything important. It's a quantitative statement, as it's not possible, I wrote this down here, to indicate whether all possible values of a feature are tested. So it just tells me how many of those kind of things I've tested. So it does not assess the legality. So the quality, again, can I do this? Am I allowed to do this? Generate package maybe randomly. Sure, I can reach the entire bandwidth, but I still do not know whether all possible lengths have been tested. A lack of execution context, so it just can run something which triggers something in the design. And yes, great, I've executed it, but did that make sense how I executed it is also missing. State of code executed or not, but not the quality It just says I have executed it, but I do not know the result necessarily. So this code coverage is very powerful, but it's not everything. Like you need both. You need a code coverage and a functional coverage. And I think that makes sense. In the test bench we talked about, we always try to do the simulative functionality, behavioral simulation, how it behaves, which you can then call as 50% or like 100%. So on the overall test, you do 50-50 on it, / both of them need to be complete to have the input. But the problem here is that functional coverage is subjective, because I write all the functions out. If I do as engineer come not up with more functions or more functionalities, more behaviors, which I just do not come up as error case or whatever, I will say this is complete, right? Like in my assessment of my point of view as I thought of the design, or even someone else thinks of the design. So there's someone else who has not written the code, but just the verification or simulation engineer will say, this is complete. So this is of course a difficult question then. So that's why you do then code coverage, to see if you have executed everything. And then you have two rules. 2 parts here, leading to 3 rules. Functional coverage is, and 100% functional coverage but less code coverage means it's either unnecessary code, so there's the code efficiency which we talked about, or, my functional coverage is just wrong because I have not executed that area, which is interesting. So there's the 2 options, which I also said already before. If something in the code is not executed, it's not being triggered, so I do not have a function which uses it. Is this because I actually do not need it, or have I forgotten a functional design part? Yes. The other way around is how I present code coverage and less functional coverage. Well, we've got to be honest to ourselves, right? We have to write our subjective functional coverage down in requirements, function 1, 2, 3, 4, 5, 10, whatever. And we need to check off, have I checked all of them properly? And otherwise I will be maybe justifying myself, I've covered everything. But in reality, we should have a list of the functions. And if I have not yet all the functions tested, but I have already 100% code coverage, then simply said the function verification is not complete yet. And so it might be that my code coverage is already at 100%, but I have not even finished testing yet. Because if I have very good code, I would use for multiple functions different combinations of states. And that would be, of course, the ideal case for efficient code. But again, this was something to look into then with the previous one, with the toggle coverage, because it will show me in the early stage, I only execute this in one state. And if the design is fairly balanced, that is a very good indicator. Of course, there's always error catching scenarios which are only maybe triggered in one scenario. But as requires to understand the code coverage report properly, you also need to understand the code. Because otherwise, I've only executed this once, great, but is it executed as it needs to be executed? That's always the big question.
Stupid question.
Yes?
I imagine a function is already a block inside the code,
Mm-hmm.
so wouldn't it be part of the block coverage already?
Yes, but the block coverage does not state so it just says it comes once. So, okay, how do I explain this? So technically, yes, the block is being executed, and I can have if-else in this block. Then, of course, this works. Then I have if-else in this block again. This would also be every line in this block executed. But what this block coverage does not consider is potentially other inputs. So in a different scenario, from another block triggered, you get a different input that might lead to a different behavior of this function block. Of course, this block will still behave as it is, but maybe there's an interference between the blocks, that I get an error, like a border and boundary scenario, so I can test this in 2 ways, either in the context of the design, which will give me all the values which I might have, or I have to random test it out. So I have to brute force every value to see if it works technically, right? Like, you don't do this, but as a logic. So you always want to consider in your design that which values do I need to consider as input, which values are relevant, and then I can go according to that. Otherwise, you have to test every signal for everything, and that's kind of inefficient.
So when I do the block coverage, I test the functions as well, but just with some example input.
I would say so, yes. I've not used this function myself so much, the coverage. Also, we will not do code coverage ourselves because those licenses are very, very expensive. So actually, you can get, you train into a test bench, and I guess you could hack in some way to get a response of how much I execute. Maybe I have a pin signal out or whatever, right? Something hacked. But in reality, there are tools, licenses, which will tell you this test bench has executed this, and this often to this extent. But we will not look into that much. That's why it's also in theory everything outlined, that you know about it. But the license costs like 10,000 euros or whatever. So.
40K.
Depends on which one, yes, exactly.
One guy.
Yes. So.
For 1 year or
Oh, no, that I don't know. That I don't know either. But, so that's why I covered it here in so much theory, so you have the context. Functional coverage, there's no license for. I mean, you can also ideally, you can map out in your like in your test bench, you can think roughly through, am I executing every block? Right, this might be a manual, might even be worth it, considering how long the design takes. But in the end, actually getting a report, you need very often a license for it. I do not know if there's any free license. Might be worse quality, but I don't know if there's anything. Yeah. Yeah, but no, sometimes it just is higher standards. Might be if something open source available, but I doubt it. It's something, let's put it this way, it's something where people want to be very sure of something, so not everyone needs it. So if a company or someone wants an actor player wants to be that sure, another company says, yeah, I can provide it, but for a lot of money. It's usually how it goes. Self-testing, just as a basically on all this top is basically functional testing almost. It automatically says, so now we come to the more stuff which we will do actually in the assignment. So self automates the verification of the outputs without manual inspection. So I do not have to go in my waveform. I may go into the waveform, of course, to understand what's happening, but I will not run my simulation. I will get a message, successful, or whatever, or these kind of errors or warnings. Oops. Techniques, assertions, reference models, and error counting. Asserts we had already, so these are comparisons of a certain signal to what I expect. Reference models, asserts in big. In a sense, I mean, I can write up, if I have an algorithm, I may write a Python script for this algorithm, and I get the response for the input values. So I write my FPGA design in Python, if that makes sense, like the function, which of course then differently processed, but the result is maybe what I want to know, and then I can compare the results to what my FPGA design gets out. So if I have an encryption, if I have a checksum, if I have image processing, I implement this the same as I do it in FPGA on my Python, and I will get the response for every of them. I run them in parallel or sequentially, whatever, and I will compare the one to another, and then I know this design works correctly. And especially useful for algorithms because you may have different test images, asserts will not work anymore. Just simple as it is. And of course, you can do error counting where you see which error scenarios you want to have. If I have an extensive test bench with extensive self-testing, which tests every scenario, every border case and boundary case scenario, whatever, we're really on the limits, I will have errors. I try to trigger those, right? So I need to count those errors, simply put, of how many I have, or I have too little or too many. Ideally, of course, would have a matrix, like to see that's actually the errors which I want, not that I have one missing, but I produce somewhere else another one, then the amount of errors is the same again. Very simple scheme, but might be useful in the overall scheme. Here are a few suggestions on increasing simulation efficiency. It's not, well, I wouldn't say it's a short list, but it's also not an extensive list. Basically, overall, it's the simulation efficiency and also in the debugging and testing, less in the verification sense. I can always adapt the simulation speed, which means the time steps. We'll come to that in the assignment. You can change the time steps in the simulation, but if I change my time step into a too big time step, I might step over a clock cycle and have an inaccuracy in my simulation. So basically the simulation speed is the time step is every 10 nanoseconds I will assess where my signals are, or every 100 or every 1 nanosecond or microsecond or whatever. So that's what I can change, and of course the more steps, the more granularity I have for a long design, for a minute for example. When my device runs for a minute and I simulate in nanoseconds, it needs to do all of those nanosecond steps to simulate and make it complete. So it's a lot of steps, which takes of course a lot of time. Always what I recommend, change your simulation to logging all waveforms. May take longer, may take, so unless you know better, may take longer, may take a lot of storage. Well, it's okay. Not more than Vivado in most designs. So not more than multiple gigabytes or whatever. Why I suggest this, even though it might be slow, is because you, especially in the beginning, you may not know, and when you debug and develop, you may not know which signal you may need. I want to dive into the hierarchy further down, and if I do not log everything, then I will not have access to that and cannot look quickly, then I have to rerun my simulation. That can be quite annoying. Of course, I can also just log certain signals. And when I say I only want to work on this IP core or on this block right now, then you may as well constrain it, but maybe you need a signal still from somewhere else to like trigger or whatever triggers, if a trigger is wrong, those kind of things. This basically depends on how much I rely on the rest of this design that I'm sure that it works, that I do not have to look at it. Because that can then, of course, increase the simulation efficiency. So logging all waveforms increases debugging efficiency, but it may reduce your actual processing time for simulation. Error logging through asserts definitely very, very useful, because you will get it when you run your simulation and there comes a wrong value back. It tells you immediately with an error, and you can stop the simulation at that point and look back, not let it run for an hour and then look at the simulation like, oh, there's one signal wrong in like the first minute, and you have waited the entire time. What I do usually tend to do is, if I do not have asserts, I look at the simulation while it runs through to see what if it corresponds to what I expect. And that of course also allows, but asserts are very comfortable in this sense. Yes. Here, this is more of a setup, systematic thing, because you can change the layout, how your simulation looks. I already showed it roughly. You can load your signals in the waveform in a certain order, as you indicated, as you have saved your configuration file or how you scriptify it, and you can give it different colors. So I might even have actually a waveform from the last simulation, which is my ground truth, which I want to compare to. Then I put it into one color, and then I put the other simulation, which is running right now, and then I can have them next to each other and can immediately see when one signal has deviated from another. So I might run my asserts. Then I see, oh, I have an error. I load the one which worked in before and put the next one, and I see immediately where it starts to deviate. That can be really, really powerful. And all these kind of things. So, or whatever is in configuration, layout, everyone also works a bit different. It's just some ideas how to make it more efficient. In the end, I would recommend for everyone to just try out the simulation tool. What can I all change? How can I make the layout? Some simulation tools allow for parallel graphs. So they like different sections which you can scroll through, so you have parallel signals. There's a lot of things possible. Everyone has their own layout. Just look through it, but those I think are the most powerful ones, the most obvious ones. Automatization, yes. We have here already had the model in the previous slide, here the reference model. Compare model automatic to test bench result. Some write the model and then they manually compare, just write the code and let it automatically compare. Most likely you will run this multiple times, and when you run something multiple times, you do not want to every time do it manually. Of course, you might end up being one of the engineers like, oh, let me automatize this quickly, and you're like 3 hours later when you could have just checked it. But we assume here that we use this test bench, this workflow for weeks, months at a time, and then it's really the upfront setup for it is really worth it. Of course, and here is one thing which may not be easy, is to resume, in quotation marks, a simulation wherever possible. The question is, of course, like, how do I resume this? Because I would need to have the state of every signal triggered on my FPGA. Do I need to change my design? Can be quite hard. What I more refer to is if I run multiple, I don't know, frames or something like this, you may be able to trigger the design into a state where it is and then continue from then to not have to simulate an hour before or something like this. So this might be very useful. Of course, also, sorry, there's one thing. And then we have simulation blocks, which basically is a golden rule. Don't verify your system as a whole until the very end. Again, we have the place and routes. You will hardly get around to test the full design because let's put it simple. If you do place and routes and you do not consider the rest of your chip design and you simulate it, is it then still place and route? Some tools may be able to do this, but why you do the place and route is because you want to consider the context, the distances, the delays in your design. Of course, a simulation tool may leave the stimulation and the signal propagation out, but it's something to really be careful about, that you do this then correctly for the last one. You can always, and that's what you actually should do, is the simpler the design, the faster simulation is the rule number one for simulation. You may want to break it all apart into many small blocks and then integrate them up, maybe, or you may go all the simple blocks and then do it all at once, depending how confident you are in your design, how many IP cores you have bought and how many you do not have to test. Because then you can run them all separately very quickly. You can make sure they functionally work. Potentially place and route you could consider, but the timing will be wrong unless you have found a way to simulate only a part of the design while the delays are still as in the big design. I honestly have not done this yet really, but it's of course possible to do probably. So this is an idea. But what you will never get around is to then, again, do it in the overall system. You just do not know how the interfaces act between each other, what responses they do. However, you may not have to, when you have, for example, an entire data stream, you may not want, or maybe you do not have to test the entire data stream. Because I know my one algorithm, my encryption here or there, this one works for the entire data stream. This will just be iteratively used. I have to only check the interfaces. So I would only just send some data through, not the entire data stream, because I would be, for the rest of the design, literally always the same processing, for example. So I put more emphasis on verifying that all my interfaces work correctly than each of the functional blocks when you have done the functional blocks separately. But as a verification approach, because you also have to consider each of these test benches and verifications also takes additional effort to do, so it's a balance to do. Like how long does my verification take? How much do I rely on my design? How do I think of this when I just need to run once place and route and it takes me days, but it takes me also days to take this design apart to make it smaller to then run the approach in a few hours. Like you need to make an assessment what is more time efficient. And having a computer run on the side is like easier than having actually man time on designing things. So this is really a very important discussion which you may even want to figure out in the beginning of your project, because at that point you will assess things and you decide already what test benches do I write, what blocks do I have, and when I write my test bench, right? So it is something which needs to be discussed early on, otherwise you will have to change everything later on or extend a lot, which then leads to cost overruns, of course. The reduce final simulation to only interface and interaction verification. Yes, exactly, that's what I just said. Yes, that was the last one. I hope I answered the questions. We definitely had the levels. Debugging efficiency, simulation speed, we had just together. How do I automatize? What metrics we had extensively. How can I generally further automatize my workflow? It's less than a lecture. It's more on the topic, sorry. It's going to be in a seminar where we load the block design through an automatic script. But of course, the simulation can also be scriptified and just run automatically. So in this case, we have covered it for the simulation. How do I make an automatic simulation? Good. That's it. Wonderful.